In these couple examples, we are looking to find a constant, right, is kind of what we're looking for. This constant is, we're looking for an a. It says, suppose that we have this piecewise function that everything is this graph, whatever that graph looks like, except at 3, because that would make a domain issue, it becomes something else, right? So the idea is to determine a value constant, this a, for which your limit as you approach 3 is actually going to equal the value. So the idea is that visually we're approaching a specific value on your limit, and when you plug in that 3, you actually get that value. So there's no hole, nothing missing. So we need this value essentially to add up to this value. And that's the idea. So here's what we're going to do. Let's figure out when you plug in 3. So first thing is, what do you get when you plug in 3? Well, this is our equation that if we plug in 3, we get an a. So not helpful, but it is helpful, actually. All right, so that's an important piece. Second thing is, so the first thing is, what is the actual y value at that? The next part of this is finding the limit. So what is the limit as x approaches 3 for this function? Well, it's actually not this, because when you're doing the limit, you're approaching it from the left and the right. So not at 3, everything but 3, right? So a little bit to the left of 3 and a little bit to the right of 3 basically means let's plug in 3. But we know we're going to have a problem, which also means there's a way to figure that out. So let's do our limit as x approaches 3. And we're going to factor this. So what multiplies to 6 that adds to -5? So a 3 and a 2, we want them to multiply to a +6 and add to a -5. So we factor the top, we factor the bottom. There's nothing to factor, but the bottom cancels. And so really, we're looking at the limit as x approaches 3. Now, once we cancel this away, that's our 0 over 0. That was our domain problem. We're really just looking at an x minus 2. So now if I plug in x minus 2, we're at 3 minus 2, which is 1. So we're approaching 1 from either side. So what should happen is that when you plug in this value, the only way that that works is that it needs to equal 1. So we're going to set the limit as x approaches 3 equal to what the y value should be. All right, so what we know is we know that that's 1. We know that this is a. So there's our answer. So our a value needs to equal 1 in order for there not to be any hole, in order for not necessarily a hole, but not in order for our limit to actually equal our y value. All right, so we'll take that same approach on all of these. So we're going to same thing. We got a piecewise. This one's a little bit different. You got linear on one side, you got linear on the other side. And then we're going to try to find determine a value constant b for which the limit uh, where it exists. So this is a little bit different, that we don't want this piecewise to have a break in, right? So rather than one side approaching here, the other side approaching here, we don't want that. We want them to be approaching the same thing. Okay, so we're going to force that to happen. And so in order to force that to happen, let's do our limit on each side and see what each side is approaching. And then we're going to force the b value to make it so they line up with each other. So if we do the limit as x approaches 2 from the left, okay, so 2 from the left would be this one. So of this function, we would have 3 times 2 minus b. So 6 minus b. Okay, and then if we do the other side, limit as x approaches 2 from the right, we'll be doing this equation. No, we'll plug in 2. So 2 minus 2 equals 0. All right, So the right side's approaching 0. The left side is approaching this kind of equation. So we're going to force this left side to equal the right side. Right? Then we know that the limit is going to exist because the limit exists if they approach the same value. So we're going to force the limit as x approaches 2 on the left to be equal to the limit x approaches 2 on the right. That's the only way the limit exists. So we know that this is 6 minus b, and we know that this is 0. So we subtract 6. Negative b equals negative 6. Positive b equals positive 6. That is what our b would be. All right, and then one last. Same idea, a little bit more complicated looking equations. So same thing, we're going to determine a value, the constant a this time, and b, that our limit is going to exist. Okay, so again, they need to line up on both sides. And so let's figure out an a that makes that happen. So we'll do the limit as x approaches -1 from the left, which would be this one, right? So this time it's g of x, which means we are taking -1 and plugging it in. All right, so we got a 1 plus 5, that is 6. Then we'll do the right side. The limit as x approaches -1 from the right, g of x. And then this time we're plugging into this, so we have a times -1 cubed minus 7. So that's -1, making that negative a minus 7. All right, so that's the best we can do here. But back to what we did here, we're going to force the two sides to equal each other because that's the only way that the limit exists. And we want the limit to exist. So our limit is as x approaches -1 from the left, it needs to equal the limit as x approaches -1 from the right. And from the left, we know it equals 6. From the right, it equals -a minus 7. And then let's figure it out. So we add 7. So 13 equals -a. So -13 would equal positive. So a would need to be -13 in order for the limit to exist. All right. So that was a couple different examples that were related to basically forcing a limit to exist by finding each side and then setting them equal to each other and solving for what you didn't know.